Welcome back after the break. My name is Martin Rosano. I come from Spain. As you can see, I'm not a Chinese native speaker, so I will not even try to pretend to be one. So it is my pleasure to present the next speaker, Professor Takafumi Hirata. He is a reference in the field of isotope ratio determinations, and he is a member of different UPAC committees, including being the chair of the subcommittee on isotopic abundance measurements. He comes from the University of Kyoto, and he has a broad expertise in using ICP-MS for isotopic analysis, particularly with multi-collector ICP-MS and using laser ablation as sample interaction technique. So I guess the topic of his presentation really fits his field of expertise. Unfortunately, I don't have any previous experience. We didn't have the opportunity to talk before, so I don't know whether he likes shopping or jogging or dancing ballet, perhaps. But what I know is that he has this very nice computer. This is the MacBook Air. You can see it. I'm very jealous about this computer. And this tells me that he likes simple and elegant solutions that just work. And probably this translates into his vision of atomic spectrometry and analytical chemistry. So, Professor Hirata, the floor is yours.
Thank you very much for your very, very kind introduction. So, and also, first of all, I have to express my gratitude for the young, May, Robert, and all of the organizers of this symposium. And it is great honor for me to be here on these special occasions. So this is the first time for me to visit China. So I'm very interested, and also I enjoy very much my Chinese food. So there are the two Chinese languages I can speak. One is Ni Hao. The second one is Was Xie Pian Jian. This is my name. So maybe pronunciation is wrong. So Rebecca's talk is very fluent English, but I'm very, very sorry that I can't speak English very much. So sorry about my kindergarten English. So maybe you have many questions, so please ask later. So today, I would like to talk just an introduction of the laser ablation ICP mass spectrometry. My talk consists of three contents. First is laser ablation. I would like to show a brief overview of the technique. And second is I would like to show the new calibration technique for the laser ablation using galvanometric optics. And third, I do want to show the future direction of the laser ablation techniques. So now we are going to first talk about the principles of the laser ablation technique. So everybody almost all knows about ICP, beauty of the ICP spectrometers. The point is ICP ion source, there's two benefits. One is a very strong ion source we call hard ionization. Almost all the elements can be ionized in ICP. And second is ICP is operating under the atmospheric pressure. So this is very, very important for us because many sample introduction techniques can be applied for. So for this is an example, schematic diagram of laser ablation technique. The sample is located, set in here. We put on the focus laser beam onto the sample surface. So evaporated or sample aerosols transport into the ICP using helium and argon gas mixtures. So the advantage of laser ablation is minimum sample preparations, no chemical decomposition, chemical purification is needed. Second is in situ elemental analysis if possible. Battery is gone. So I will use another pointer. And also in situ elemental analysis is possible using laser ablations. So this is, I'm afraid that I'm geochemist. Okay. So we have doing a lot of in situ elemental and isotope analysis using laser ablation. And finally, the high masses throughput can be achieved. For example, we are doing some zircon dating. Zircon is one very famous tough zircons, tough samples, quite difficult to develop in acid. So many geologists ask me, we do want to measure zircons, for example, 100 zircons per day. So before there's ablation, we can measure only 7 zircons per week. That means only 1 zircon per day. It's just a bit tough work. But after the developed there's ablation technique, we can measure almost 50 to 100 zircons per day. Is not so difficult. Because it's too difficult to do that. So the highest analysis throughput can be achieved by the laser ablation. So this is a brief overview of the history of the laser ablation technique. You can see the recent 10 years, the laser ablation development is achieved by the shorter wavelengths. So the first instrument is ruby lasers, now going to neodymium lasers, four harmonic generations producing to 66 nanometers, now partially available to 13 nanometers. Also, X-ray lasers producing 193 nanometer wavelengths. So the recent 10 years, laser ablation technique is developed using shorter and shorter wavelengths. So what is the benefit to use shorter wavelengths or UV wavelengths is as follows. One is stable signal intensity profiles. I'll try to show an example of the time profile later on. Second is the reduction in the elemental fractionation during the laser ablation. It's also very important to obtain a reliable data. Third is ablation head from small areas. So we are now using 10 micron ablation head. So this is very, very, very powerful to measure the zircon dating from small zircons. So this is key, very, very important. So these features we can achieve by the UV lasers. Now I want to show the difference in the time profile of the different wavelengths. So this example of the time profile, the signal intensity is plotted against time. So we can show if the sample is at mix 612, it's a glass tangle. If you ablate using laser to 66 nanometers, this is the first commercially available wavelengths of the UV wavelengths of lasers. It's produced by the fourth harmonic generation of neodymium lasers. So signal intensity, we can obtain a very high intensity, but signal is not stable, decaying, and so there's small spikes we can see. But when we using a much shorter wavelengths, signal stability is improved, and also the intensity only going up. But much better signal stability can be achieved when using a much shorter wavelengths. When we're using 193 wavelengths, signal stability is much, much better, and almost there's no signal spikes can be found. Why is that? Why is stable signal intensity can be obtained? The reason is very simple. This is a diagram showing a size distribution. Sorry about that. This is size distribution of the laser-induced sample particles. This is the size. This is the number of particles. This is the size of the particles. If you're looking at the distributions, when you're using a shorter wavelength, something like that, the size distribution can be modified toward smaller sizes. So this is very important. For example, we call the size of the sample sizes from the 0.2 to 0.4 microns. We call this the critical size. If the size of the particle is larger than these sizes, all the sample particles cannot be completely atomized and ionized. So some sample is passing through, survive in the ICP, so this producing some signal spikes. So we have to use this size of a much smaller size for the analysis. So when we introduce small size particles, all the particles can be atomized, ionized completely in the ICP. So this is very important. So we have to produce the smaller size distribution. This is very important to obtain reliable data. So UV lasers, the most samples, for example, minerals, glasses, ceramic, and also amorphous samples, we can obtain very good data. However, in case of the metals, we can't measure because This is an example showing example of the time profile obtained from the electric couplers. This is intensity plotted against the time. So you can see there's a lot of signal spike there. So this is, in this time profiles, we can't measure any reliable reproducible data. So why the lot of signal spikes coming from? The reason is very simple. In the case of the metals, the metal has free electrons. The free electron has very, very fast discharging the laser energies. So if you're looking at the temperature of the electrons, the laser energy is fast transferred to the electron of the samples. Then the electron transfer the lattice, that means vibration of the atoms. So this is the temperature of the atoms. So the fast laser energy is transferred to the electrons. The temperature, maximum temperature until 116 degrees, then decay. So because thermal energy is transferred to the lattice, so as you can see, there is very tiny but a flat region here. So this means that something is melting. Okay? So molten sample is splashed away by the laser-induced shock wave. So this is a picture showing the splashing the molten phase. This is sample. This is high-speed image. As you can see, the resolution, you can see that many particles releasing from the ablation pit. You can see that. So this means that the size of the particle is larger than 1 micron. This is, of course, larger than critical size. So if the sample is releasing from here, going to the ICP, that can cause all the signal spikes in times of profiles. The point is, we have to control how to produce small sizes of subaerosols. So this is another suggestion of the development. So now, using femtosecond lasers. So femtosecond lasers is time duration for the laser pulse is much shorter than the conventional nanosecond lasers. So this is much more effectively we can ablate metal samples because the pulse length, the typical pulse length of the femtosecond lasers is something like 100 femtoseconds or 200 femtoseconds. This is much shorter than thermal diffusion of metals. So that means that even with the metallic samples, we can evaporate something effectively. So we can obtain the data or small particle sizes even from the metallic samples. So this is a comparison of the time profile obtained from the couplers. In the case of conventional nanosecond lasers, you can see the unstable signal intensity and lots of signal spikes here. And also, a lot of deposition can be found around the ablation pit. However, when we use femtosecond lasers, the signal intensity is enhanced almost 5 to 10 times. The stability is much more stable signals can be found. And also, there is almost no deposition on the ablation pit. So this is the beauty of the femtosecond lasers.